Okay, so in this video, we will do a quick summary of everything we have studied in this chapter. So this chapter was about vector spaces. Okay, so what have we studied in this chapter? Let me give you a quick summary. We start the chapter with the concept of a vector space. We have defined vector space and we have seen the 10 conditions a space must obey in order to call that space a vector space. Okay, then we move on to subspace. Okay, we have seen that a subspace is a subset of a vector space that is itself a vector space. Okay, then we move on to the spanning sets. And we have seen the link between a spanning set and a subspace. We have said that a spanning set is a subspace. Okay. We have then seen the concept of linear independence. And we have said that vectors of a set are linearly independent, or a set is linearly independent if the only way we can write any linear relationship between the vectors of that set is when the coefficients are zeros. Okay, so when the coefficient, the c's, are zeros. Number 5. Oh yeah, the next concept was a basis. A basis, and we have defined a basis as the set. Okay, basis of a vector space is a set that is linearly independent and that spans the space. Okay, and we have seen how to represent a vector in a basis with respect to a basis. Representation of a vector with respect to its basis or a basis. Number 7, we have seen the dimension of a vector space, and we have said that the dimension of a vector space is the number of the element in each spaces. And then we move on with the row space as the span of each rows. Then the row rank is the dimension of the row space. Okay, and we have seen the column space and the column rank. Okay, and we have finished. We know how to find the row space. What do? We perform Gauss method, and then the basis of that row space is going to be the non-zero rows, and the rank is just the number of the element in that basis. For the column space, what we do is we firstly transpose the column. So to find the basis for the column space, we firstly transpose the matrix, perform Gauss's method, and transpose back the column. Transpose back the matrix, and then take the non-zero columns as being the element of the basis of the column space, and the column rank is just the number of elements in that basis. Okay, and we finished this chapter with the rank of the matrix, and we have seen that beautiful theorem that says the rank of a matrix is the rank of its column space. which is also the rank of each column space. Sorry. So basically, in summary, the theorem says that the rank of the column space of a matrix is equal to the rank of the row space of the matrix. So the row rank and the column rank are the same for a matrix. Therefore, the rank of a matrix is either the column rank or the row rank. So to find the rank of a matrix, you can just find the row rank, or you can just find the column rank. But you can go one step further. What we have to do, or what we do to prove that the row rank and the column rank are the same, or sometimes you want to find simultaneous a basis for the row space and the column space, you just perform Gauss-Jordan method and you bring the matrix to reduced echelon form, and you write for the column rank, you write the columns with the leading entries, and for the row space, to find the basis for the row space, you just write down the rows with the leading entries. Okay, so you can find the row rank and the column rank simultaneous by performing Gauss-Jordan method. Okay, this is going to be the end of this chapter. Thank you, and see you in the next chapter, the third chapter. Thank you.